In this video, we are going to explore the relationship between amount in and volume of a gas, and this relationship is described by Avogadro's law. So once again, the results that we find here again coincide with our common everyday experience. Simply put, the amount of gas increases as volume increases. Okay, so they're directly related. The more gas you have, the more volume it's going to occupy, assuming that you keep pressure and temperature fixed. So what we see here is a plot in red that shows the number of moles of gas, right? And we are progressively increasing the number of moles of gas, and we find that the volume also increases. Okay, so I'm going to make a little note here that we do, of course, have constant pressure and temperature. Okay, so under these conditions, we see a nice, clean linear relationship. So this solid red line here shows a nice, clean, linear relationship that says volume is directly proportional to N, the number of moles of gas that you have. Okay, so once again, we can express this relationship by saying that this ratio of volume over N is equal to some constant. And so that ratio, V over N being equal to a constant, is something that's going to always hold, right, for any given state that you happen to be in. So any initial state, final state, state 1, state 2, right? So that allows us to write out a nice simple relationship which says the volume over number of gas molecules or gas phase atoms is going to follow this sort of relationship here. V over N is always going to be equivalent. Okay, so let's see how we can apply Avogadro's law here to solve a couple simple problems. So let's start off first, right, using our little relationship here to solve the following problem. Let's suppose that we triple the amount of gas and we're going to hold pressure and temperature constant. Okay, so we're just tripling the amount of gas. Then according to Avogadro's law, what change would we expect to see in the volume of the gas? Okay, so let's go ahead and write out everything that we know. So we know that we're going to be starting off at some initial volume, right? And we've got some initial amount, and then we are changing the system by tripling the amount of gas. So we're going to be here at some final state 2, and we're going to have an N2 that's equal to 3 times N1. And we want to ask the question then, well, what do we expect to see in terms of the behavior of that second volume, that V2? Okay, so we're going to use, of course, Avogadro's relationship here, which tells us that V1 over N1 is going to be equal to V2 over N2. We're going to be solving for V2, right? So if we solve for V2, we get V2 equals N2 V1 over N1. Okay, then we know that the final number of moles of gas, N2, is actually 3 times N1. So we have 3 times N1 is V1 over N1. So then we're going to go ahead and cancel out number of moles of gas. We will then arrive at 3 times V1. Okay, and therefore what we are going to predict is that if you triple the amount of gas that you have, then you will be effectively tripling that initial volume. So V2 is going to be 3 times that initial volume, which of course is what we would expect given the linear relationship that we observed in this previous diagram. Okay, so now let's go ahead and tackle another problem. And this problem introduced a little complication, so we're going to have to read it carefully, but we're going to basically apply Avogadro's law to a more detailed quantitative problem. So in this problem, we're told that a male athlete has a lung volume of 6.15 liters during a deep inhalation. Okay, so presumably somebody that exercises a lot has a really strong lung volume, really large lung volume. At this volume, we're told that his lungs contain 0.524 moles of air. Right? During exhalation, right, breathing out, his lung volume decreases all the way down to 2.55 liters. What we want to figure out then is how many moles of gas that athlete exhaled. Okay? And of course, we're going to assume constant temperature and pressure. Okay? All right. So first thing we want to do, we know we're going to be using Avogadro's law, right? So what we want to do is write down the given information, right? So we know that initially, this male athlete has inhaled. We know that initially the volume is going to be 6.15 liters. And we know that initially then this athlete has 0.254 moles of gas. Then exhalation occurs and the lung volume decreases to 2.55 liters. Okay, and then we are being tasked with figuring out how many moles of gas did the athlete exhale. All right, well, the N2 here, right, we don't know what N2 is, but N2 is going to tell us how many moles of gas are left in the lungs. Okay, this is not how much gas is exhaled. Okay, so the first step is going to be to solve for N, the number of moles of gas that are left in the lungs, and then we're going to have to take the initial number of moles, right, the 0.254, and then subtract off the amount of moles that left the lungs, okay, and then that will give us are left in the lungs, and that will give us how many moles of gas that athlete exhaled. Okay, so this is another tricky point that I see students get stuck on. Right, you might be very comfortable with Avogadro's law and setting up the ratios and solving these problems, but you have to be very careful when you're reading these problems to make sure that you are analyzing very carefully what the question is asking, and then taking any extra steps as needed in order to make sure that you are getting the right answer. Right? Okay. So once we've identified that little sticking point there, then it becomes a relatively straightforward Avogadro's law problem. We're going to use our ratio of volume over amount, solve for our N2. We're going to plug in our 2.55 liters, right, for that final volume. We're going to plug in our initial volume right down here, 6.15 liters, and the initial number of moles, okay, the 0.254. We will then solve for N2, okay. Then to find the moles exhaled, we're going to subtract that moles left over in the lungs from the initial number of moles that were present to obtain our final answer. Okay, so to sum things up, we have Avogadro's law, which basically tells us volume and amount are directly proportional. We use that to build up a nice little relationship here, right, that just as we saw for Boyle's law and Charles' law, right, allows us to predict changes in either the volume or amount, right, under conditions where pressure and temperature are constant. All right, now that we've explored all of these individual relationships, Charles' law, Boyle's law, now Avogadro's law, we're now in a position to go ahead and put all of these relationships together and build up the so-called ideal gas equation. And so the ideal gas equation, the construction and application thereof will be the subject of the next video.